Yes, welcome Professor Karvembu.
Yeah, good afternoon. Can you hear me, Dr. Vengat?
Yes, it's
Yeah,
clear.
good.
So, shall we start?
Yes.
Yes, yeah. So, Professor Karvembu is the second speaker, and he's now a professor at National Institute of Technology, Tiruchirappalli, India. He holds a doctorate degree in chemistry from Bharatiyar University, Coimbatore. His extensive research spans coordination chemistry, organometallic chemistry, catalysis, and bioinorganic chemistry with international recognition, including visiting professorship in Japan, UK, and Austria. He has more than 200 research articles. He has made groundbreaking contributions in both basic and applied fields, particularly in the development of effective catalytic systems for industrially important reactions. His work spans diverse areas, including sustainable catalysis, anti-cancer compounds, and design of electrocatalysts. He holds memberships in various professional bodies and has earned numerous patents and awards. So with this introduction, I invite Professor Karvembu to deliver his lecture.
Good afternoon, all of you. I thank Professor Vengat for his kind introduction. Actually, I had planned to come there and deliver a talk in person till today morning. Then after I entered into airport, I found the flight is delayed so much, and I felt I might not reach the venue on time. Then I canceled the flight. I came to my institute back and now giving talk online. I'm going to share some of the results that we have obtained in our laboratory with respect to the electrocatalytic conversion of carbon dioxide. And this, there is a urgent need to prevent climate change and its consequences. This is the very important goal in the sustainable development. The global average of atmospheric carbon dioxide is above 400 ppm, which is too high. And the surface temperature has already risen approximately 1 degree centigrade since the pre-industrial era. And because of this, there are a lot of severe consequences. And the present target is to limit the global warming by 1.5 degree centigrade. For this, we have to achieve net zero by 2050, and the previous speaker, Professor Jay, explained this very nicely. And to achieve this net zero, we have to reduce the emission as well as we have to accelerate the removal of carbon dioxide and other greenhouse gases from the atmosphere. So we can get fuels or hydrocarbons or some useful chemicals from carbon dioxide electrocatalytically. From that way, we can find some solution for the removal of carbon dioxide from the atmosphere, or from this carbon dioxide, we can obtain some useful products. And for this purpose, we have chosen metal organic frameworks as electrocatalysts. Metal organic frameworks are porous, crystalline, organic, inorganic hybrid materials. We have been utilizing these metal organic frameworks as catalysts for various organic transformations. And because of the superior properties of these metal organic frameworks, they found applications in various fields. One of the important applications of MOFs is in catalysis. And these metal organic frameworks have been modified after its preparation without affecting its original crystal structure. That is called as post-synthetic modification of MOFs. There are various ways in which the MOFs can be modified. The metals present in the MOFs can be replaced by other metals. The organic linkers can be replaced, or both metals and organic linkers can be modified. We can add the metal based gas molecules into the metal organic framework, or we can incorporate some organic based molecules into the metal organic framework to modify the properties of the MOFs without affecting its original crystal structure. We are interested in modifying the MOFs by introducing an organic molecule into the MOF. And for this purpose, we have selected Riboflavin, and this is not the first time that MOFs are used as electrocatalyst for the reduction of carbon dioxide. If you look at the literature, bismuth indium bimetallic metal-organic frameworks have been used to prepare bismuth indium bimetallic nanoparticles on carbon networks, and which has been used as an electrocatalyst for the reduction of carbon dioxide to formic acid. Similarly, carbon single atom catalyst has been prepared from carbon based ZAF metal organic framework. And here, if you look at the way, the method they have used to prepare the metal organic frameworks or the final catalyst, they have adopted energy consuming methods like pyrolysis or calcination. But we wanted to prepare metal organic framework in aqueous medium at a very ambient temperature without adopting any energy consuming methodology. And then the post-synthetic modification of MOF or the use of modifying MOF in electrocatalysis is also not new, and not only in electrocatalysis, for in other catalysis also. And the Vialogen, a photoactive molecule, is used to modify an MIL series of MOF, and the Vialogen modified MIL has been used as an photocatalyst for the reduction of carbon dioxide. So keeping this in mind, we have used the vitamin B2 or riboflavin to modify the MOFs. Now initially we have modified the nickel MOF with the help of riboflavin without affecting the original crystal structure of the MOF, and this has been used as an electrocatalyst for oxygen reduction and oxygen evolution reactions, and this catalyst has also been used in some biomass conversions like conversion of HMF into FTCA. Now motivated by the results we have obtained from this post-synthetically modified MOF, we have prepared a copper-based metal organic framework. Copper is well known as electrocatalyst for carbon dioxide reduction reactions. Now copper in different forms give different products from the reduction of carbon dioxide. That is very interesting. So using 4,4-bipyridine, we have prepared metal organic framework under very ambient condition at very ambient temperature in aqueous medium. This metal organic framework has been characterized by using various spectroscopic techniques. You can see here we could get single crystals of this copper based metal organic framework, and we could solve its structure. Copper is octahedrally surrounded by 6 ligands, and there are 2 nitrate ligands, 2 water, and 2 coordination sites are occupied by nitrogen atoms of bipyridine ligands. And after the preparation of this copper MOF, it is modified with riboflavin by means of simple mixing or grinding this MOF and riboflavin. And this is a simple mechanochemical synthesis method and done by means of mortar and pestle. The color of the copper MOF is blue color, and once you mix it with riboflavin, the color is immediately changed to green. And we have utilized the pristine copper MOF as well as the riboflavin modified copper MOF as electrocatalyst, and these two materials have been characterized by means of different techniques to first understand even after the modification the structure of copper MOF is changed or it is not changed. And if you look at the power XRD patterns of pristine copper MOF and riboflavin modified copper MOF, we can understand that the patterns are very similar, so there is no change in the crystal structure of the copper MOF even after its modification with riboflavin. And we have measured the bed surface area, and bed surface area of the pristine copper MOF is 79 meter square per gram, and that of riboflavin MOF is 40 meter square per gram. So there is a considerable reduction in the bed surface area, indicating that the the guest molecules, that is the riboflavin, occupied the surfaces of the pristine copper MOF. And then we have characterized the materials by means of U visible and FTIR spectroscopic techniques. And if you look at the riboflavin modified copper MOF, there are some absorption bands between 300 and 500, which are characteristic of riboflavin, that indicates that riboflavin is incorporated into the copper MOF. In the IR spectra, we found the NH asymmetric bending vibration in the riboflavin modified copper MOF, that is due to the presence of riboflavin. And these are some characterization techniques that gives an idea that riboflavin is incorporated, and without affecting its crystal structure. And we have analyzed the surface morphology. So from XPS analysis, we could confirm that the oxidation state of copper present in the MOF is +2, and interestingly, that these are the XPS spectra of riboflavin modified copper MOF. The photo emission peak at 933 electron volt is clearly split after the modification of this riboflavin. That gives an idea that the copper ions present in the MOF interact with the riboflavin. So, but there is no such split observed in the case of pristine MOF. And we have used cyclic voltammetry and linear sweep voltammetric techniques to understand the electrocatalytic property of the pristine copper MOF and riboflavin modified copper MOF. And by using copper MOF as catalyst in the presence of nitrogen saturated 0.5 molar sodium bicarbonate electrolyte, you could see a very slight increase in the current density. But when we have used carbon dioxide saturated electrolyte, a prominent increase in the current density was observed. And when the electrolyte is saturated with nitrogen, still there is a slight increase in the current density that might be due to the hydrogen evolution reaction. But when we have used carbon dioxide saturated electrolyte, there is no hydrogen evolution reaction, but the reduction of carbon dioxide happens, that leads to prominent increase in the current density. But if you look at the cyclic voltammograms, when this riboflavin modified MOF was used as a catalyst, in the presence of carbon dioxide saturated electrolyte, you can see the current density is greater, that is very close to -12 milliampere per centimeter square. So it clearly indicates that the riboflavin modified copper MOF is a superior catalyst for the reduction of carbon dioxide compared to the pristine copper MOF. Then we have analyzed by means of linear sweep voltammetry, particularly to understand the proper ratio of copper MOF and the riboflavin. Initially, we have taken 1:0.5, one copper MOF and 0.5 equivalent of riboflavin. And when this material is used as an electrocatalyst, the current density is around -10 milliampere per centimeter square. When we have increased the amount of riboflavin, it means the ratio is 1:1, then the current density is very much greater, that is very close to -14 milliampere per centimeter square. Then further increase of riboflavin, that is the ratio is 1.2, then again the current density comes down, again close to -10 milliampere per centimeter square. Maybe that the more amount of riboflavin, if it is added to the MOF, that might block the metal sides of the MOF. So we take 1:1 as the optimum ratio between copper MOF and riboflavin, and this ratio is further used to conduct the further experiments. We have also calculated the Tafel slope, and for the riboflavin modified copper MOF, we have observed a very less stable slope, that is 269 millivolt per decade compared to the pristine MOF. That indicates the faster reduction of carbon dioxide in presence of this riboflavin modified copper MOF electrocatalyst. And this is just comparison of bare glassy carbon electrode, pristine copper MOF and riboflavin copper MOF. You can see this significant reduction over carbon but slight reduction is observed over copper MOF, and the reduction is prominent. We could observe from current density when we have used riboflavin modified copper MOF as a catalyst. And we have also calculated the resistance by using the electrochemical impedance spectroscopy. When copper MOF, pristine copper MOF was used as a catalyst, the resistance was close to 3 ohm. But the modified copper MOF showed the resistance of only around 2 ohm. So it means that the modified copper MOF decreases the charge transfer resistance, so that facilitates electron transfer across electrode electrolyte interface. We have also analyzed the electrochemically active surface area from the cyclic voltammograms run in non-Faradaic region, and we have calculated the double layer electrochemical double layer resistance. And in the case of riboflavin modified copper MOF, the electrochemical double layer resistance capacitance is around 600 microfarad per centimeter square. But when we have used a copper MOF as a catalyst, the capacitance was around 160 microfarad per centimeter square. It is closely fourfold increase in the capacitance when the modified copper MOF was used as an electrocatalyst. That indicates that more amount of ions can be absorbed onto the electrode surface, right, when the riboflavin modified electrocatalyst was used. So that might facilitate the more amount of reduction of carbon dioxide. And from the chronoamperometric analysis, we can see that at minus 1.8 volt, we could observe higher current density, and we have run this chronoamperometry for 2 hours, and this gives the stability of the system also. We have calculated the Faradaic efficiency at different potential, and at minus 1.8 volt, the Faradaic efficiency of the system when we have used the riboflavin modified copper MOF is 90%, whereas the Faradaic efficiency of the pristine copper MOF is around 60%. So there is a significant enhancement in the Faradaic efficiency when we have used the riboflavin modified copper MOF as a catalyst for the reduction of carbon dioxide. So this gives the selectivity of the reduction process. And we have used proton NMR and carbon NMR techniques to analyze the product obtained from the reduction of carbon dioxide and also to quantify the product obtained. From the H1 NMR spectra, we could identify the formation of formic acid. We have observed a chemical shift at 8.3 ppm that indicates the formation of formic acid. We could also observe a meager formation of methanol. And from the C13 NMR, again we have observed the formation of this formic acid from the chemical shift value at 160 ppm. So these are the spectra obtained when pristine copper MOF was used as an electrocatalyst. But these are the spectra obtained when riboflavin modified copper MOF was used as an electrocatalyst for the reduction of carbon dioxide. And we have quantified the amount of carbon dioxide formed using the NMR technique, in which DMSO was used as an internal standard. And we could find that we have obtained 300 microliter of formic acid during the electrochemical reduction of carbon dioxide. But now by using the saturated carbon dioxide in the given electrochemical conditions with riboflavin modified copper MOF, we could observe 300 microliter of formic acid. And here you can see that at minus 1.8 volts, at different, we have collected the sample at different times, and you can see the progressive increase of the formation of formic acid during the electrochemical reduction of carbon dioxide. And even here, there is no much difference in the intensity of the signal at minus 1.8 volt and minus 2 volt, right? It looks similar, and so we took minus 1.8 volt as the optimum potential for the reduction of carbon dioxide to formic acid, and that potential is used in further experiments. And we thought that the enhanced activity of the riboflavin modified copper MOF is due to the inherent electrical characteristics of the material, because the riboflavin itself is known for its electron transfer properties. It involves in various electron transfer reactions in many biological systems. Interestingly, we have analyzed the used catalyst. After the experiment, we have removed the catalyst and we have analyzed it by means of TEM. And you can see the copper MOF has been converted into the particles after the electrochemical experiments. The particles may be copper or copper oxide. Still, we are analyzing the nature of the particles by means of XF. Now, you can also see the riboflavin modified copper MOF. There are no formation of the particles even after the electrochemical experiments. It means that it is not only the inherent electrical characteristics of the riboflavin modified MOF, also the riboflavin enhances the stability of the copper MOF, right? So even after many cycles and the long duration of the catalysis, we could observe that there is no change in the structure of the copper MOF once riboflavin is introduced into the copper MOF. So this might be also one of the reasons for the enhanced activity of the riboflavin modified copper MOF in the reduction of carbon dioxide into formic acid. And we have shown that compared to the pristine MOF, and the riboflavin modified MOF can act as a better catalyst for the reduction of carbon dioxide to formic acid. And we have prepared the MOF and we have modified the MOF under very mild conditions, and we have quantified, we have analyzed the product, and we have also quantified the product, and the Faraday efficiency of the catalyst is found to be good. And I would like to thank Dr. S. Pandiraj, who was my PhD student, who is currently working as a postdoc at Uppsala University, Sweden. I thank the funding agency SED, my institute NIT Trichy for providing the facilities. I thank the organizers of Energy Summit for giving me an opportunity to present our work in this platform. Thank you. You can ask if you have any questions.
Thank you, Professor Karvembu. It's time for questions and discussions. You have the, if there are none, Professor. Yeah, Professor J has a question.
Yes, yes.
Really fascinating talk. Why is it you think that the copper MOF disintegrates when you do your electrocatalysis of CO2?
You are asking where it is disintegrating, then it is disintegrating?
Yeah, why is it? Because you've got your riboflavin, which is doing the catalysis, that's not causing any problems at all, so you're getting the whole structure being integrity maintained.
Correct. So because we think that the riboflavin interact with the MOF through some kind of coordinative interaction with the copper ion. We found that some of the stretching frequencies corresponding riboflavin is modified after it is incorporated into the MOF. So there is a kind of coordinative interaction between copper and riboflavin that might stabilize the copper MOF.
And if you were to change it from copper to, say, iron, would you get the same degree of catalysis with the current still? So is it which would be an exciting thing to try later on at some point?
Yes, later on. And before this, we have tried with nickel MOF, but not for carbon dioxide reduction. But we have tried in oxygen evolution, oxygen reduction, and some biomass conversions, where also we have observed that this riboflavin stabilized the nickel MOF, but it's a good idea that we can also try with the iron MOF.
Yeah. So it's then seeing whether the copper's electron density comes all the way through onto the to the CO2, or whether it's, if within the nickel case, whether it's just stopped and you get the classical nickel behavior. No, that's fantastic. Thank you. Really enjoyed listening to it. Thank you.
Yeah, I think Professor Ranjit has raised his hand. So, Professor Ranjit.
Good afternoon. Thanks, Venkat. And he's my friend. After a long time, I am seeing him through one line. Anyway, the question is, actually you are focusing more on formic acid, and surprisingly it is very much precise. The formation of formic acid is only component you are showing. But when we are going for any CO2 reduction, there are various byproducts, and formic acid is one of the products which we need. So on what way you are targeting only formic acid, and why there is no other byproduct in your presentation?
That is interesting, and what we have got is mostly formic acid, but as I have shown that we could also observe some meager amount of methanol, but we have observed only formic acid and methanol, no other product during the course of the reaction. So that is very interesting, and of course the copper is known for its selectivity in the electroreduction of this carbon dioxide. But as I said in my introduction, copper in different forms give different, selectivity towards different products. And when we have used MOF, we found selectivity towards this formic acid.
What we can do so that it can, what type of adduct or what type of molecule we can attach so that it can go to methanol or ethanol concept, because higher density, it will be better for us to get into the energy market, particularly in terms of C2 or C1 product. So how do you want to go ahead in that direction? Is it MOF is possible to go in that direction?
Might be. So there are some MOFs reported which selectively gives methanol. Actually, we have also tried to tune the catalyst, since we have already observed the formation of methanol in the reaction, and we did some modification and we tried to get methanol selectively compared to the formic acid, but we could not succeed. And maybe we should modify the catalyst as well as the potential range of the electrocatalysis. We have to tune both to get the methanol or some other products to get selective.
Okay, thank you. Thank you very much.
Welcome.
Thank you. Any questions? Yeah, I have a quick question, Professor Karvembu. So when you do this mechanical milling of the MOF and the riboflavin, how do you ensure that the riboflavin is quantitatively incorporated into the MOF structures? Or do you always, have some of it is left behind and then you proceed ahead with whatever is incorporated and then do rest of the stuff?
Yes. Okay. Yes. Yeah. Yes, but from the XRD pattern, we could observe there is no free riboflavin present.
Okay. So that is also there along. Okay.
Yes.
Yeah, so then how do we remove it actually in case if you have to take the PR stuff to the next stuff? What are the...
And of course, we have proceeded with whatever incorporated. We have not much focused on the removal of the remaining RBF.
Okay. Thank you, Professor Karvembu. You have one? Quick, yeah.
Sir, in CO2 electrochemical reduction in CV, one reversible oxidation peak in copper MOF, but that is not in riboflavin copper MOF. Oxidation peak around minus 0.4. Yeah,
Yes.
this one. Minus 0.4 volt. The one oxidation peak is there in.
Yeah, correct. No, that is, no, this is a metal based one. And just a minute, I have to move this. And this is a metal based one, and here the potential of this is altered. Now that is one indication that there is a coordination interaction between the riboflavin and the copper MOF that altered the potential of the copper.
Okay, sir. Thank you, sir.
Thank you, Professor Karvembu. If there are no questions, once again, let's join thanking Professor Karvembu for this wonderful presentation. Thank you.
Thank you very much, Dr. Wenger.
So the session is over. Now we can disperse for lunch. Thank you for all the speakers who have participated, and thank you for all the audience who have been interactive. Thank you.